A gardener has 480 feet of fencing to fence in a rectangular garden. On one side of the garden, it's bordered by a river and so does not need any fencing there. What dimensions would guarantee that the garden has the greatest possible area? Okay, so what we have to do is decide first what it is we're trying to maximize or minimize. When we're optimizing, we are either doing one or the two. So here we're trying to maximize area. So we want to maximize, and we need some sort of formula for area. So we're trying to maximize area, and this is based off of a rectangular garden. So area for a rectangle is length times width, which I'll just say x times y here. Now, setting dimensions to any numbers, we could make really large gardens if we, allowed the length of the fence to be 5,000 feet on one side and 15,000 feet on the other. But the thing is, we have a constraint. So there are constraints in our problem. And constraints reduce us to only being able to make a garden of a maximum size. All right, the constraint is that we basically only have 480 feet of fencing to fence in the garden. Now, if that's the case, any fencing that we put up, and we were told that we could do the fencing along this side and along this side and along here, but we didn't need to put any along the river because it's just not necessary. So the total of these three distances is going to be 480. That's the maximum. And that's a perimeter. So we have to think about that as our constraint in terms of perimeter. So 480 is going to be, I'll say this distance here, well, I'll use that as the horizontal variable. So this distance here would be x, so going this way, and this distance here would be y. Now, if you'll notice, x times y still gives me area, but to get 480, I don't need any fencing along the river, so this is going to be similar to the concept of perimeter, but not exactly. I only need 2 dimensions of y plus 1 dimension of x, because I only need to go on one side of the garden. All right, now, in order to solve this, what we do is try and change our formula that we're trying to maximize, which right now has 3 variables, a, x, and y. We want to get it down to 2 variables. So we can rewrite x in terms of y or y in terms of x through our constraint. And that's the idea here. So potentially I could say, and you can use either one. Let's see here. I could say that x is equal to 480 minus 2y. So I've just moved the 2y to the other side, and that gives me some way of expressing x in terms of y. And then what that allows me to do is replace into my formula up above for area. So x, which is now 480 minus 2y, I can replace that, and then multiply by the same y variable that I had. Okay, so right now I've got the area dependent on the value of the variable y is going to be 480 times y minus 2y squared. And if you'll notice, this is a quadratic. And quadratics have a turning point that indicate a minimum or a maximum, depending on if it's opening upward or opening downward. This one is in fact opening downward, so it would be a maximum, which is what we want. To find where that minimum or maximum occurs, we invoke the derivative. So we find the derivative with respect to y. So this would be 480 minus 4y. We set that derivative to 0 and solve for y. So negative 480 equals negative 4y. And if I divide, let's see, 480 divided by 4, so 120, yeah. I come up with y has to be 120 feet. And by my diagram here, it looks like the shorter side should be the 120. I'm not going to answer that for the shorter side just yet until I verify through the formulas. But I can use this and figure out what the longer side is through the constraint formula, because right here, I know that x is 480 minus 2 times whatever y is. So if I know that y is 120, then 480 minus 2 minus 2 times 120 is 240. So that means x is 240, and that is, so y is my shorter side, so 120 feet. The longer side is 240 feet. The greatest possible area, we would take x times y and multiply those together, and that would be the maximum area, 28,800 square feet.